Hey everybody, we're going to start out today with a demonstration on standing sound waves. So being cooped up at home all day, every day, I had to improvise with the materials a little bit, but this is very similar to what we do if we were in class. So I've got a pitcher of water, and then I'm going to use this paper towel tube that's already wet. So the tube I'm going to use to contain the sound wave. And then the water is used, I'm going to put the tube in the water, and then when I raise and lower the tube, that will change the length of the air column, because the surface of the water is going to be the closed end, and then we've got the open end up here to let the sound in. Okay, so similar to standing waves, or similar to the waves in open end tubes and on strings, you could send any frequency you want down this tube. But there's only certain frequencies that will create a standing wave within those conditions. Okay, so what I'm going to do is I've got my phone set to a specific frequency, 350 hertz, and then I'm going to change the length here until we get that standing wave. Now remember, a standing wave is when the reflected wave overlaps the incident wave, and that is resonance. And if you remember, resonance creates a big amplitude, and a big amplitude for sound means loudest. Okay, so again, I've got this set to 350 hertz. I'm going to change the length of the column until we hear that loud point. That's when we know we have a standing wave. Okay, so let's get this one started. All right, I'll put it right on top here. So you see a point right about there is the loudest tone. Hear it quieter here, and it goes through that. So right here we've got a standing wave. Now what would happen if I change the frequency? Okay, let's try that. Okay, so there it's pretty quiet, right? So it's not creating that standing wave anymore. So I'd have to change the length of the tube to get the standing wave for that frequency. Okay, so each length is going to have a different frequency that creates the standing wave on that. All right, now I did the math, and I know that's the first harmonic or the fundamental frequency. We're going to look at that in a minute. But in the previous video, we went through that simulation for the standing waves with sound. So if you remember that, great. If not, I put a link in this video too, so check that out again, just review that before we move on. So now we're going to look at how to solve for the different frequencies that will create resonance or standing waves under certain conditions. All right, we looked at this slide in the previous video, but we're going to go through it again real quickly just to make sure we remember everything. Okay, so when a wave goes from one medium to another, some of that energy gets transmitted into that other medium and some is reflected back. And we're looking at that reflected part. Displacement node exists at the closed end and antinode at the open end. Again, we saw that in the simulation. So similar to standing waves on strings, only certain frequencies will create standing waves given those conditions. We've got two types, open at both ends, like a flute recorder or a pipe organ, and then closed at one end, open at the other end, like a saxophone or a trumpet or wind instruments like that. We're looking at the closed end, so this screen should look familiar. Similar to what we did with the open end, but this is closed at one end. So you see how it's closed at one end like that. All right, so we're going to look first at the lowest frequency or the fundamental frequency that will create a standing wave in a certain length of closed end air column. So again, we want the lowest frequency, so the biggest wavelength. We're going to stretch this standing wave out, knowing that there has to be a node at the closed end and an antinode at the open end. So that's going to look like that. Okay, now we need to determine how much of a wavelength we have here. Okay, so again, only look at one part of it. We start at equilibrium and we get to a crest. Okay, but a full wavelength, we keep going back to equilibrium, down to a trough, and then back up to equilibrium. That would be a full wavelength. So if you look at this carefully, you should see we have a quarter of a wavelength or a fourth of a wavelength here. Okay, so the wavelength really is 4 times the length of this air column. Using V equals F lambda, we put in 4L for the wavelength, and then we solve that for frequency. So just divide by 4L, and we get F1 equals V over 4L. Again, V by default 343 meters per second unless you're told otherwise, and then L is the length of the column. You'd either be given that or that's what you're solving for. So F1 again is called the fundamental frequency or first harmonic. Okay, so now let's increase the frequency. I wasn't able to do this with the demo, but let's increase the frequency, and that will decrease the wavelength. So we're going to squish this wave down until the next antinode gets to that open end. So that's going to look like that. All right, so now how much of a wave do we have here? Well, we start at equilibrium, go to our crest, back to equilibrium to a trough. We need to get back up to equilibrium and complete one wave. So it looks like we're at 3/4 of a wave. Okay, or the wavelength is 4L over 3. All right. Now, I know some of you take this very seriously, and right now you're yelling at your computer saying, hey, you missed this one. All right, well, that was intentional. We'll see that in a minute if you don't see that coming already. So we're going to go to the wave equation again, V equals F lambda, and plug in 4L over 3 for the wavelength. And then we're going to solve this for frequency, and we get 3V over 4L, which is 3 times V over 4L. V over 4L is our first harmonic, so 3 times that must be the third harmonic then. Okay, so that's why I skipped that second one there. Okay, so let's increase the frequency again, decrease the wavelength, so the next antinode gets to the open end of the tube there, and it's going to look like that. All right, so we've got 1 full wavelength and then another quarter. So 1 1/4 wavelengths, or put it in a fraction, 5/4. So the wavelength is 4/5 the length of this column. Go to V equals F lambda, put in 4L over 5 for the wavelength, solve that for frequency, and you see it's 5 times V over 4L. So this must be the 5th harmonic. All right, so a little bit different from the open end, because the open end, we had every harmonic. Here, we only have the odd harmonic. So what happens with the second and the fourth? They don't exist. It just won't happen there, okay? So this is a little different than the demo I did. The demo, I held the frequency constant and then looked for the length to get that standing wave. Here, we kind of have a set length, and we're looking for the frequency to get that standing wave. It all works the same, though. All right, so quick summary for closed end. There's a displacement antinode at the open end, displacement node at the closed end. Any harmonic is given by n times the first harmonic, but in this case, we only have odd harmonics present. So keep that in mind if it's closed end, and I'm looking for like the second lowest frequency, that's really the third harmonic. So don't get tripped up by that. Just with the open end, I recommend that you start with the first harmonic. It's easiest to draw. Again, if I give you the 27th harmonic, you're going to sit there a long time trying to figure that out. And then plus to interpret that gets pretty confusing to count the wavelengths and all that. So, all right, let's do an example. Okay, I think I'm going to have to move myself out of the way. Yeah. Okay, so air in a closed pipe resonating in the third harmonic. Make a note of that. Frequency is known to be 440 hertz, the length of the pipe 60 centimeters. What is the speed of sound? And is this a warm or a cool day compared to room temperature? All right, so again, we're going to start with the first harmonic. So I'm going to draw that picture first. So it's going to look like that. The more consistent you are, the easier these become. Okay, so how many wavelengths do we have here? Well, it's 1/4 of a wavelength. We looked at that in the last slide. So the wavelength is 4 times the length of this column. Go to our wave equation, V equals F lambda, plug in 4L for the wavelength. So V equals F times 4L. Okay, now we need to remember that our picture is based off the first harmonic. So when we get this expression, this is really the fundamental frequency, or that first harmonic frequency. Keep that in mind. Now we're told the frequency of 440 hertz is the third harmonic. okay? But our equation is working off of the first harmonic, so we need to figure out what that first harmonic is. So the third harmonic is just 3 times the first harmonic. So we can divide that 440 by 3, and we get that first harmonic frequency, or the fundamental frequency. Now we can use that number in the equation we just developed. Okay. So we've got 146.7 is our first harmonic, the fundamental frequency. The length is 0.6. We've got the 4 down there. We solve that for V. I'll move me out of the way. So 352 meters per second. So if you remember, 343 meters per second, that's the speed of sound at room temperature. And the temperature, the higher the temperature, the faster sound travels in air. So we have something greater than 343 meters per second, so we know it must be warmer than room temperature. And I calculated this, and I forgot the number already. I think it's in the 90s or something for degrees Fahrenheit, so a pretty warm day. Okay, all right, that's it. Subtle differences between closed-end and open-end air columns, but start off with a good picture. Know you have an antinode at the open end, a node at the closed end. Always work off of that first harmonic, and you should be in good shape. Let me know if you have any questions.